Hello ladies and gentlemen, in this video we're going to compare mass, weight, and gravity. These are related topics, but they are not the same. So as you probably recall, mass is the amount of matter in an object. The symbol for mass is an M, and we measure it in kilograms. Mass is a property of an object, or it's a property of material, and it always stays the same value, even in different gravitational fields. This balance in this picture shows that we have an accumulation of mass on both sides. It's the same amount of mass, and if we pull this up, it shows I have this quantity of zinc, this quantity of sulfur, and whether I move them around or not, it's still going to be the same amount of mass if I alter this. So mass is a property of a material. Weight, however, is related to mass, however, it's not the same. So the definition of weight is that it's the downward force created by gravity on a mass. The symbol is F sub g, and its unit is in Newton. The pound, the unit we usually think of in the United States is a pound for weight. However, we won't be using that in our science class. But you can think of a Newton as like a pound. It's the same sort of a measurement. The equation for weight or force due to gravity is mass times acceleration, or mass times the acceleration of gravity g. And the weight depends on the different values of the gravitational fields. So, you've been watching this dog float around over here. The dog is weightless, or appears to be weightless, because he's on a space station. He still has mass, but we don't see any force of gravity acting on him. So that's why he floats around. If we think of mass versus weight, and we look at these two astronauts, and answer the questions listed on the right, we know that mass and weight are different, so we want to differentiate between them. So does the mass of an object change from the Earth to the moon? So we have this astronaut. His mass is 120 kilograms in both places. It's the same astronaut. So no, his mass does not change because mass is not affected by the gravitational fields. So no, does the mass of the object change? It does not. Does the weight of an object change between the Earth and the moon if we're dealing with the same object? And yes, it certainly does. The weight of this astronaut on the Earth is 1,200 newtons. The weight of the same astronaut on the moon is 200 newtons. So yes, the weight of the astronaut changes since the gravitational fields are different. The gravitational field of the moon is less. It's not as strong as the Earth, so the astronaut weighs less on the moon than he does on the Earth. Okay, this next question is kind of a silly question. If you wanted to lose a lot of weight, how could you do it really fast? Well, since your weight is related to the gravitational field strength, if you go to the moon, then you're going to weigh 1/6 of what you do on the Earth. Your mass is still going to be the same. You're not going to be any smaller, but your weight will be dramatically lower. Okay, let's do some practice for calculating weight. Remember, to find weight, we take mass times the gravitational field strength. So for the first one, this is we're going to find out how much something that it has a mass of 68 newtons, how much that weighs on the Earth. So on the Earth, a 68 Newton object would weigh 666.4 newtons on the Earth. The same 68 kilogram object on the moon would weigh 108.8 newtons. So 1/6 as much, since the gravitational field strength is smaller. Now let's predict, will the object weigh more or less on the sun? We have a stronger gravitational field, so the 68 Newton object should weigh a lot more, and it does. It weighs 18,591.2 newtons on the sun. Now, clearly the sun doesn't have a surface. Anything that would be on the sun would burn up, but it could still feel a gravitational force near the sun's surface equal to this value right here. Okay, Mars has a gravitational field strength. It's about one third, roughly one third that of the Earth. So the 68 kilogram person would weigh 251.6 newtons on Mars, and Jupiter is much more massive than the Earth. So a 68 kilogram person would weigh 1754.4 newtons on Jupiter. So as gravitational field strength increases, then weight will increase. As gravitational field strength decreases, weight will decrease, even though mass is the same throughout. Okay, so this is an interesting study of gravity. We're going to look at a little video here where we talk a little bit about how gravity actually works in the universe. But gravity is just the overall pulling force that's created by masses when they interact with other masses, because all objects with mass have a gravitational field. So you have mass, so you actually have a gravitational field. You don't have very much mass, though, so your gravitational field is extremely small, really immeasurable. It's so small it can't be measured. But when objects are extremely large, extremely massive, like the Earth, then they develop gravitational fields that are significant, and those gravitational fields affect the motion and create significant forces on the things around them. The symbol for gravitational field strength is a G, and the unit, since gravity, the acceleration of gravity is an acceleration, so the unit is meter per second per second. And as I stated before, every object with mass has a gravitational field, but more mass means more gravity. So listed along here, Jupiter is more massive than the Earth, therefore its gravitational field strength is greater. The Moon is less massive than the Earth, therefore gravitational field strength is smaller. There's one other factor that affects gravitational field strength. It's actually the radius, but we won't get into a whole lot of that. Let's look at this space-time video. This is really interesting. It shows one of the ways that astronomers can look at what's happening with planets and infer that there are objects that we can't see, like black holes or planets that are difficult to look at. Sorry, I missed it. There we go. Okay. So according to Newton's first law, things travel in a straight line unless there's an unbalanced force acting on them. So this shows up a marble moving in a straight line. There's no gravitational force acting on it. So if we imagine that this is space, then when something moves in a straight line, then we assume that there's no gravitational fields acting on it. But when we have things like planets, they can create gravitational fields and create what's called a warp in space-time. So this very large, massive ball is put toward in the middle of this, and we'll see how it affects the path of objects that move. These two objects will accelerate toward each other. That's pretty predictable. But this one's rather interesting. And the fact that we're going to see a physical object, but gravity can actually deflect light, as the slide said. So sometimes scientists observe that there are planets because the light bends, much like we saw the path of that ball just bend. So this is an example of an object that moves in an elliptical orbit. This again is another really good way that scientists can locate the presence of celestial bodies that it can't see. So if the orbit velocity is just in the kind of a sweet spot, and just the orbital speed, exit orbital speed, then we'll get an orbit that's relatively circular. And this is much like the Earth's orbit around the sun. The Earth's orbit around the sun is slightly elliptical, but it's an ellipse with not much eccentricity, so it behaves more like a circle. The Earth really isn't much closer to the sun at any point in time than any other time. This is interesting. So this shows kind of an Earth-Moon relationship where the smaller marble will rotate around the big pink mass, but it also rotates around the large larger marble as well. So this shows us dark energy with a kind of a crest here. So this has exactly the same effect. It just simply has, it just is kind of warping space the other direction. So this is kind of fun to see how this works. So if there's a large mass in the center and then lots and lots of masses like asteroids moving around, then they will create order. Look what happened. They all came from different directions, but now they're all spinning in the same direction. These guys didn't try to favor that. They just pushed them together. Let's look at that again. Marbles were just thrown in, randomly thrown in. And they just created through entropy a preference for a clockwise rotation. And that was just by chance. They could do it again, and it could end up with a counterclockwise rotation, depending upon the arrangement of the masses and the way they collided. Okay, so that's kind of an interesting demonstration of some of the sorts of things that astronomers can observe in the atmosphere. So you had lots and lots of things we covered in this video, so watch it again if you need a review.